Welcome to The Explainer. Today, we're diving into something absolutely crucial for site technicians and engineers. We are translating Majesh Kumar Manikam's QA/QC protocols from @QA/QC Pro Academy into a practical, step-by-step field guide for inspecting flange gasket seating surfaces. If you work around industrial pressure vessels or piping systems, you already know that a compromised seal isn't just an inconvenience, right? It's a massive safety and operational hazard. So we're going to build a chronological checklist that you can take straight into the field with you. All right, let's get into it. 1.5 millimeters, or, about 0.062 inches. It is tiny! We're talking barely the thickness of a standard ID card. But listen, if the gap between the raised faces on a ring-type joint, an RTJ flange, drops below this specific tiny number, your inspection stops right there. At that exact point, you immediately have to start considering repairs or remachining. We'll get into exactly why this threshold is so unforgiving in just a second, but keep this number in your head as we go. So, here's our game plan today, your ultimate field sequence. First, the pre-disassembly RTJ gap check. Second, flatness and cracking inspections. Number 3, understanding radial defect widths. 4, hard versus soft gasket limits. And finally, engineering reviews and repairs. Let's start right at the beginning with Section 1, the pre-disassembly RTJ gap check. Before you even think about putting a wrench to that joint, the standard clearly states you've got to examine the gap between the outer edges of the raised faces. Remember that 1.5 millimeter threshold we just talked about? This is exactly where it applies. You need to check this gap at locations all the way around the joint's circumference. Why? Because maintaining this minimum gap guarantees the flange faces won't physically touch during assembly. If those middle faces do touch, the gasket isn't compressing properly, and boom, you've got a major primary cause for a leak on your hands. You catch this before the joint is even opened. Okay, assuming that gap is good to go, we move on to Section 2, flatness and cracking inspections. So, you open up the joint. That's step 1. Step 2, get in there and inspect the actual seating surface for any physical damage. We're talking pitting, gouges, that sort of thing. But step 3, well, this is where you need to be hyper-vigilant. You must inspect that gasket groove specifically for cracking, using the right inspection technologies. This is an absolutely vital safety protocol. A crack in the groove isn't just some minor little defect, it is a critical hazard that completely destroys the structural integrity of your seal under pressure. Now, to physically check if that surface is flat, you use what we call T1 measurement lines to figure out the circumferential variation. Basically, you set a datum and take measurements all the way around that circular track to find the maximum acceptable difference between the highest and lowest points. If your flange is warped or distorted, maybe from extreme thermal stress, this T1 measurement procedure is definitely going to reveal it. Circumference is checked, so let's zoom in a bit for Section 3, understanding radial defect widths. Following the ASME PCC-1 guidelines, we really need to nail down 2 terms here to evaluate the micromeasurements of our damage. First, we have RD, or radial defect. That's literally just the width of the damage cutting across the flange face. And second is W, the face width, the total width of the seating surface itself. So we're evaluating these defects based on a simple ratio. How far across the face does the damage stretch? Also, actually, make sure you remember this. Defect depth is always measured from the highest peak of the surface finish straight down to the bottom of the gouge, never from the average surface, always the peak. When you're figuring out the radial variation, notice how your measurement line needs to go straight across that gasket seating surface, from the inside edge directly to the outside edge. You're looking for differences across that specific radial path. When you spot a scratch or a gouge spanning across this line, you measure its width, that is your RD, and compare it to your total width, W. All right, you've got your measurements. Now we hit the go or no-go phase. Section 4, hard versus soft gasket limits. You're definitely going to want to mentally bookmark this quick reference table. It essentially translates all those complex engineering formulas into simple fractions, like less than a quarter of the face. Just look at how the allowable defect depth practically vanishes as the defect gets wider. If your radial defect is less than a quarter of the face width, well, you've got a little leeway. But as it stretches from a quarter to a half, for a hard gasket, that depth can't be more than 0.25 millimeters. That is literally nothing. It's basically a heavy scratch. So what this really highlights is the massive difference in compression characteristics. Hard gaskets, they are incredibly sensitive to flatness issues. I mean, virtually zero margin for error here, mostly because they just don't compress easily into those tiny surface imperfections. Soft gaskets, on the other hand, are a bit more forgiving. They have more give, so they can tolerate slightly deeper defects and still provide an effective seal even if the surface isn't totally perfect. But, and this is a massive but, there is a hard stop. Defects spanning more than 3/4 of the face width are absolutely 100% never allowed for any gasket type. It doesn't matter if you're using a hard gasket or a soft gasket. If a gouge crosses more than 75% of your seating surface, that is a glaring red flag. That flange cannot safely seal under any circumstances, and trying to assemble it is literally just asking for a failure. Which naturally leads us into our final section. Section 5, Engineering Reviews and Repairs. So, what happens when things go wrong? If your inspection uncovers gasket groove cracking, if those T1 and T2 flatness limits are totally exceeded, or if your defect depths push past the maximum thresholds we just covered, your field inspection is officially over. You can't just treat these as failed metrics on a clipboard. These are impending leak pathways. They have to trigger an immediate escalation. And once you escalate, all the guesswork goes right out the window. Standard ASME protocols kick in, and you must refer to PCC-2, Article 305 for specific repair considerations. No improvising quick fixes out there on the floor. You have to rely on standard engineering codes and professional judgment to properly assess the risk and figure out the exact standardized method to repair or remachine that groove. I want to leave you with a final question to chew on. Is your flange truly ready for pressure, or are you just assembling a leak? If you follow this structured checklist from that very first pre-disassembly gap check all the way down to those strict depth limits, you take the guesswork totally out of the equation. You make sure every joint you close is actually sealed. Keep these checks in your back pocket next time you're out in the field. Thanks for tuning into this explainer, and we'll see you next time.